our last lecture, we looked at philosophical questions that arise in the context of cosmology, physics on the largest scale possible. For the next several discussions, we'll move to the other extreme of the size scale and examine the philosophical ramifications of the physics of the small. Ultimately, this will lead us to the weirdness of quantum mechanics. But we need to take a half step first to get there. In the classroom, I often do the following exercise. I ask the class, okay, so who believes in the existence of Santa Claus? There'll always be one person who raises her hand, unwilling to surrender the joy of her childhood. Then I ask, okay, so who believes in the existence of atoms? All the hands go up. I ask, who's seen Santa? Well, we've seen drawings of him and people dressed like him, the class answers, but no one's ever really seen him because Santa Claus does not exist. I ask, who has seen atoms? One or two hands go up. You've seen atoms, I ask? Well, there are electron microscope images that show them, and I've seen those images. Oh, so you mean you interpreted the results of output that was interpreted, and the interpretation then printed in a way that makes it look like it's a picture of things? Well, yes, but... So really, it's even less direct evidence than seeing the fat jolly guy in the red suit at the mall. Well, yes, but... For those who did believe in Santa at one time, I then ask, why did you acquire that belief? Well, my parents told me and the cookies were gone and the presents were there, so it seemed reasonable. So, on the grounds of authority and inference from best explanation, yes. And all of you who believe in atoms, why did you acquire that belief? The class uncomfortably admits because their teachers told them, and it explains lots of things. So, you believe in atoms for the same reason you used to believe in Santa Claus, but Santa Claus isn't real? They uncomfortably admit that this is the case. At this point, I simply say, welcome to philosophy. And that is our question. Why should we believe in the existence of atoms? The question about the nature of matter has been a fundamental question since classical times, and we have great confidence in the atomic hypothesis. Is such confidence warranted? And even if it is, should the theory be literally interpreted? Notice that this is a question for all of physics, not just atomic physics. When we have a theory that works well, can we make the inference beyond working well to actually descriptive of reality? In philosophy of science, we call this the question of realism. And what we want to look at now is the question of realism in terms of the unobserved entities we call atoms. The atomic hypothesis, of course, well predates contemporary physics. In classical Greece, thinkers such as Democritus and Epicurus argued that matter was composed of basic particles, atoms. The word atom means uncuttable because they would be the smallest part of all material things. The question in ancient times was, how many times could I take a thing and cut it in half? The atomists contended that it was a finite number of times. Eventually, you would get down to a bit that had no parts and therefore couldn't be cut again. The entire universe on this view is comprised of an empty void and basic, uncuttable, unified atoms bounding about within it. We've been socialized with this idea, making it seem commonsensical to us. To many classical thinkers, however, it was patently absurd. The arguments against atomism still seem quite strong. Classical atomism claimed that there were two things, atoms and the void. As such, there were two lines of attack. One argued that there were no smallest bits of matter. If I cut my way down to an atom, a sharp enough knife would let me cut it in half. Hence, no matter how small you cut it, you can always still divide it. Therefore, there are no atoms. The other objection held that a void, what we would call today a vacuum, is impossible. There were many arguments. Since the void is itself a thing, positing the absence of a thing where there is a thing is self-contradictory. Space can't be empty if it's filled with space. Or, since air is a substance, if you try to remove air from a region, more air would just flow in. Today, these arguments seem quaint, as they did in the 16th and 17th century when the idea of real scientists considering them undermined the rise of science. Atoms at that time smacked of the sort of naive metaphysics that authentic science was seeking to overcome in being truly rational. To speak about atoms, uncuttable, invisible particles, was embarrassing in a scientific context that was trying to base an entire worldview on the principle that seeing is believing. So, how did atoms go from an embarrassing, childish metaphysical fantasy of speculative philosophers who had no experimental data to an accepted truth in the hardest of the hard sciences? How did we come to believe in atoms as a scientific, not philosophical truth? The evidence came from two different directions, physics and chemistry. Now, these were two different scientific communities and had different reactions to the notion. Physicists were in general quicker to warm to the idea than chemists. From Newtonian mechanics, physicists were used to dealing with abstract point masses, that is, treating things as dimensionless, frictionless, idealized object. The atom was just a materialized version of the Newtonian point mass. Chemists, on the other hand, have long had physics envy. Physics seemed a more developed science with a more quantitative theory behind it. Chemistry developed out of alchemy, which left a taint on chemistry of magical hocus pocus. Chemists longed to have as rigorous a science as physicists, and to talk about invisible little particles reminded everyone of the alchemical history of the science that it was trying to eliminate. Chemists did not want to talk about anything that could not be directly observed or measured. The evidence from the physics side came from the study of the physics of materials, especially gases. Thermodynamics examines how properties of heated bodies behave. The idea that heated bodies were just made up of tiny little bodies in motion appealed to physicists because it put chemists out of business, making all of chemistry just a branch of physics. In the 1730s, Daniel Bernoulli, one of the giants of 18th century physics, first proposed the idea of a kinetic theory of heat. That is, that heat is just a result of motion. It slowly gained momentum with physicists, but the chemists disliked it, in part because it diminished chemistry. Chemistry was the science of substances. You could not reduce the property of substances to a bunch of billiard balls bouncing around. That sort of reductionism went too far. Heat, we long thought, was not a property of substances, but was a substance itself. Many classical views of the nature of matter classified heat or fire as a basic substance. Aristotle's worldview did, and as Aristotle became the official doctrine of the Catholic Church, most European scientists did as well. And it makes sense, right? Look at a sidewalk on a hot day. What do you see? Heat flowing out of it. Put something near a fire, and it heats up and changes form or changes its properties. Why? Because you added something to it. Seeing is believing. And we see heat and what adding heat does. We even had a cool name for the stuff, phlogiston. When Joseph Priestley discovered oxygen in the 1770s, he thought that it was dephlogisticated air. Air was a substance, heat was a substance. Take the heat stuff out of the air stuff, and what you got was this new pure substance. This air without phlogiston could do lots of interesting things. Put a glass jar over a burning piece of paper, and the paper would quickly stop burning. But then add some dephlogisticated air, and poof, the flame came roaring back. Clearly what happened was the air inside the jar had reached its full phlogiston capacity and couldn't take any more out of the paper. So the phlogiston flow, that is the flame, stopped. But add dephlogisticated air and more phlogiston could flow out, thus the return of the flame. Now around the same time, Antoine Laurent Lavoisier was thinking differently about that sort of experiment. He reran Priestley's experiment with burning paper and dephlogisticated air and found that the ashes of the burned paper were heavier, not lighter, than the unburned paper. Phlogiston theory had said that the fire of the burning paper was the paper giving off phlogiston. How could something giving off a substance end up heavier than when it had it? One possible explanation is that phlogiston has negative mass. Negative mass? Put that in potato chips and you'd make a fortune. But more likely, what it meant was that something was being added to the paper in the process of burning. Lavoisier formulated the principle of the conservation of mass, that mass could neither be created nor destroyed, and concluded that the gas was adding something to the paper in the process of burning. That something would turn out to be oxygen. Priestley and others were starting to find all sorts of different gases that had different properties. If there were different kinds of air, then Aristotle's simple picture of earth, air, fire, and water as the basic list of substances was far too skimpy. It became seriously difficult to keep up with all the different sorts of air that were being created through various chemical means. Add to that Lavoisier's undermining of phlogiston theory, and with air no longer a single substance and heat not a substance at all, suddenly the questions began to multiply for the chemists. The different versions of air were created from different reactions with different chemicals. It seemed that the different sorts of air were made from particles which comprised them. In the early 1800s, Joseph Louis Proust and John Dalton noticed that the recipes used to create the different sorts of chemical reactions had an interesting property. They required amounts of substances in simple proportions. When you look at hydrogen and oxygen and ran electricity through them, you got water, for example. It would take twice as much hydrogen as oxygen. Any more hydrogen and it wouldn't be left over. It just wouldn't convert. It had to be 2 to 1, no more, no less. Simple numbers. Nature is rarely clean. If there are integers involved, it probably means that it's the number of something. When counting numbers show up in science, it usually means there's something there to be counted. The law of multiple proportions implied that beneath the seemingly continuous substances we saw lurked a discrete reality. The ultimate number related to all these substances was derived by Lorenzo Romano Amadeo Carlo Avogadro. His great discovery was that if you held the pressure and temperature constant, then the mass of the gas would be directly proportional to the volume. If the atomic hypothesis were true, then we could use this fact to determine the relative molecular weights of the molecules of the gas. It also followed that at a standard pressure, temperature, and volume, there would be a specific number of molecules. It would be called a mole of the substance, and the number itself, of course, would be known as Avogadro's number, about 6.022 times 10 to the 23rd. We had long known that there were certain regularities that held between thermodynamic properties of temperature, volume, and pressure. Boyle's law, for example, said that if you take a gas and squish it, it gets smaller. Deep, I know. But the point is, there's an inverse mathematical relationship between pressure and volume. We can combine this law with those of Charles and Gay-Lussac and the new insight from Avogadro into one big equation called the ideal gas law, PV equals nRT, better known to chemistry students everywhere as PVNRT. What's important here is that P, V, and T, pressure, volume, and temperature, are measurable macroscopic properties. R is just a number, a constant to make the units come out right, but N is the number of microscopic entities. This law connects the empirically observable macroscopic world with the invisible, theoretical, hypothetical microscopic world. It was at this point that the physicists picked the game back up in earnest. In the 1860s, James Clerk Maxwell had a series of papers designed to show that matter was comprised of what he called molecules. What Maxwell does in his first paper is to start from the assumption that gases are made of molecules. He further assumes that these molecules are perfectly spherical, infinitely hard, and interact only through contact. That is, are purely mechanical with no electrical charges. If temperature is a measure of the kinetic energy of those particles, and pressure is the result of the force of the collision with the container, then, Maxwell showed, that the behavior of the collection of these tiny little billiard balls is exactly what we observe in the behavior of gases. If we take gases to be made up of molecules, hypothetically, then they would have to behave almost exactly the way we know real gases actually behave. It would be absolutely miraculous if this was an accident. Of all the ways it could come out, it just happens to be this way? Given that we don't believe in the miraculous, we should believe Maxwell argues that gases are made up of molecules. But notice an important step in the argument. To make the mathematics manageable, he assumed that the molecules were perfectly spherical, infinitely hard, and not electrically charged. He knew that these assumptions were false. Real molecules would not be like this sort of idealization. It's an idealization. That's why it's called the ideal gas law. It holds exactly only for ideal gases. How many ideal gases are there? None. They're imaginary approximations. Yet we have a law about them. We're deriving scientific principles about things that don't exist. What's next? Unicornology? Yet, from this law about something that Maxwell full well knew doesn't exist, Maxwell's saying that we have good reason to say that molecules, something we've seen as many times as we've seen Santa Claus, do exist, unlike Santa Claus. He addresses that problem in the next two papers, where he slowly de-simplifies the model and shows that with each new complexity, new empirical results that we had previously observed become explainable. We're able to explain more and more the better and better we make our molecular approximations. So, Maxwell concludes, we should believe that matter is made up of bits. Still, many were unconvinced, including some big-named, highly respected scientists. Invisible tiny particles as the basis for science is as bad as positing leprechauns as forces in our theory. It was not scientific. Then, in 1905, along came Einstein. In one of 5 papers he wrote that year that changed the world, Einstein worked with statistical reasoning to show that he could explain the strange behavior known as Brownian motion. Discovered by Robert Brown, the idea is that if small particles of, say, dust are suspended in a liquid, say water, and you look at them through a microscope, they move. Not smoothly as one would think from currents or heat flow, but randomly. Particles near each other would exhibit completely different motions. What was causing it? Some had suggested that it was the collision of the molecules of the water hitting the dust particles, but particles were so much bigger and heavier than the molecules of water that, even if they did exist, it'd be like trying to move a truck by hitting it with a balloon. But Einstein realized it wasn't individual molecules, but a constant barrage. We would need to think of this statistically. And he did, and showed that if the water were made up of molecules whose speed was dependent on the temperature, then we could calculate the force imbalance that would cause exactly this sort of random zigzagging that we see. He derived observable results. Well, observable in principle. It would be really hard to actually do it. It would take unbelievable patience and precision. It would take Jean Perrin. In 1913, Perrin did exactly the experimental work, and it turned out that Einstein's calculations were right on target. The combination of Einstein's theory and Perrin's experiment is widely held to be the final blow that nailed down the existence of atoms. For his work, Perrin was awarded the Nobel Prize. In his book Atoms, where Perrin explains his work and his inference, he also showed a hobby that he shared with Einstein: collecting derivations of Avogadro's number. The two of them were always on the lookout for new and different ways of coming up with an equation that contained Avogadro's number and other quantities that could be measured. They found them in a wide range of completely independent ways, from different starting principles in different areas of physics, yet always ending up with the same number. That seemed to say that the number is real. And if the number is real, and it's a number of things, then surely that also means the things are real. And that is how we came to believe in the reality of atoms. How we came to believe it is a matter of history. Should we believe it? That's a different question. That question is philosophy. Philosophy of physics launches with the logical positivists, and the figure at the vanguard of the logical positive movement was Rudolf Carnap. One of the goals of logical positivism was to clean up the human belief structure, to lose all the old superstitions, all the old false assumptions, all the old intellectual clutter that was getting in the way of our seeing what really is true in the world. They sought to remove everything that wasn't directly observed. Carnap proposed doing this in the most direct and effective mode possible by limiting the language of science to that based on direct observations. If I say, there's a chair in front of me, what that really means is that there is a logical combination of protocol sentences which is equivalent to what would be the case if there were a chair in front of me. The term protocol sentence means an observation report of the most basic sort. Brown here now, smooth here now, hard here now. The idea is that these were sentences that are confirmable by direct observation. Combine them and you get the complex experience of seeing a chair reduced to the most basic set of operations of the simple uses of the senses. We would have constructed the notion of a chair from our simple experiences. Most importantly for Carnap, we can now completely determine the truth conditions for the sentence, there is a chair in front of me. We now know how to determine which sentences can be empirically confirmed. Those sentences are meaningful. Meaningful sentences that are confirmed are true. Meaningful sentences that are disconfirmed are false. Sentences that are not meaningful are nonsense. Much of philosophy, especially metaphysics, is not able to be reduced to logic and protocol sentences, and therefore is meaningless nonsense that should be thrown away. The junk that philosophy has been using to clog up the intellectual works for centuries could now be removed, allowing for progress through a scientific worldview. Atoms were a significant problem for Carnap. There doesn't seem to be a way to build the notion of atom as we use it in physics out of basic observation reports. The concept comes out of our scientific theories, and we want rational belief to be guided by scientific theories that are well supported by evidence. But there's not a straightforward way of making sense of these theoretical terms. Theoretical terms are those parts of the theory that are not directly measurable, are not mathematical formalism, but are needed as part of a scientific theory. The problem is that with theoretical terms like atoms, science wasn't just creating confirmable laws connecting measurable properties. With terms like atoms, science was making metaphysical claims. Carnap wanted to eliminate metaphysics, replacing it entirely with empirical science and logic. But to his chagrin, science seemed to keep on reintroducing metaphysics, foiling the plan. This conundrum, especially with respect to atoms, led to some of the younger logical positivists and students who had been drawn to the logical positivists to begin to part ways. A new movement arose that sought to put metaphysics back into human knowledge, under the condition that it came in through science. This new movement is called scientific realism, and it holds that, 1, we ought to interpret our best theories as probably true, that is, as descriptive of the world, and 2, the theoretical terms in those theories are part of the furniture of the world. That is, if a central term is essential to one of our best theories, we ought to think of it as real, even if it's unobservable. The first condition was clearly problematic because everyone wanted to hold that science progresses. Our best theories now will, no doubt, be replaced with new, better theories someday. And those would be replaced with newer, better theories afterwards. That's just how science works. But then, no theory is true. How can we hold science to give us truth, the central element in scientific realism, If we know all scientific theories are born false, just a link in a chain, we hold the best theory at any given moment to be approaching truth. With each new step, we get closer to having truth. It's an asymptotic process where each new best theory is approximately true. But what's important for us in this discussion is the second element, what we call entity realism. It holds that the machinery of the best current theory should be thought to reflect the actual constituents of reality. Our best theory of matter employs atoms in it, so we should believe that atoms exist. One of the leading figures in scientific realism had one of the greatest names in the history of philosophy. The two best philosopher names are the Cambridge philosopher John Wisdom and the Australian philosopher J.J.C. Smart. The scientific realist was smart, very smart. Smart argues that we might be able to do logically what Carnap wanted to do in eliminating all non-observable entities from our best scientific theories. Let's say that our best theory of matter, atomic theory, is called T. We very well might be able to create a subtheory, T prime, which is comprised only of observable terms, no non-observables like atoms, and do it in a way that the empirical predictions of T prime are exactly the same as those of T. In other words, we might be able to take our best theories, axiomatize them like mathematicians do, and reduce them to just relations of observables. Smart's response is, so what? Does this make atoms unnecessary? Does this make atoms just useful fictions? Are atoms nothing but helpful ways of thinking but not actually connected to reality? He says no. To hold that this logical maneuver eliminates atoms as real would be like a detective finding bloody footprints leading to a murder weapon and then think that the notion of a suspect is just a useful fiction. The suspect is real. He's a person who committed the murder. Atoms are just as real for the same reason. They're the mechanism that explains the observed relation of the macroscopic properties. To believe in the laws that Maxwell derived without believing in the microscopic entities he used in the derivation would be to believe in what he terms a cosmic coincidence. Does everyone then buy into scientific realism? Are philosophers united in the position that belief in atoms is rational? Of course not. We're philosophers. In opposition to scientific realism, Bas van Fraassen, a professor at Princeton, offers a very different picture of science, which he calls constructive empiricism. In his book, The Scientific Image, Professor van Fraassen contends that while the positivists went too far, so too do the scientific realists. There's a tension between empiricism, that we ought to derive all our views about the world from observation, and metaphysics, that we can say something about what's real in the world. Carnap's project didn't work. That doesn't mean that we surrender to the new metaphysicians. Van Fraassen starts by saying that we want to accept our best theories. He says that he accepts atomic theory. But what's entailed by this acceptance? If you accept it, do you think it'll never be overthrown by a better theory? No. So accepting it doesn't mean thinking it's true. A new theory might force us to throw away our idea of atoms. So again, what are we accepting when we accept the theory? Professor van Fraassen says that all we're doing in accepting the theory is agreeing that it's empirically adequate. That is, we believe that everything observable that the theory predicts is or will be observed. The function of physics is not to pull back the curtain on the invisible inner workings of reality. It's much more modest, to give us good tools to make predictions and organize our knowledge. When we accept the theory, we're saying it's a good tool. It does its job. Scientific theories and the entities they contain are constructed by physicists, not discovered. Atoms were made by physicists, not uncovered. And it's a darn good thing they were, because they're really useful tools in constructing a great theory. But if we asked our theories to do too much, if we asked them to tell us exactly what the invisible world really looks like, then we risk going too far and telling the invisible world how it has to be. The scientific realist may overstep his scientific bounds. The result of this could be that the world refuses to have the microstructure the scientific realist demands it has. This, Professor Van Fraassen contends, is exactly what happens when atomic theory gives way to quantum mechanics. Quantum mechanics creates all sorts of problems for the scientific realist. What are these problems? Well, that'll take several entire lectures to set out and discuss, and of course those will be our next 3 lectures. See you then.